కెమెరా ఒకసారి చూసుకుంటూ వెళ్ళి స్టార్ట్ అయినప్పుడు ఇట్లా పెట్టేసి ఓకేనా. Hello guys, welcome back. See, please try to note down the timings and the subject wise timings and the dates. Today after analog electronics 12 to 1 p.m. you will have control system, 5 to 6 power electronics, 7 to 8 electrical machines, and tomorrow 20th August 10 to 11 English, 11:30 to 1:30 GA, 5 to 6 quantitative aptitude, and 7 to 8 measurements, right. Coming to the today's topic, analog electronics guys. If you see the syllabus as compared to the TS GENCO and the TRANSCO and or earlier AP GENCO TRANSCO, there are some difference changes in the syllabus of analog electronics part. One topic which is operational amplifier have been removed. Okay, so operational amplifier and timers, 555 timers have been removed. ఈ ఆపరేషనల్ యాంప్లిఫైర్ అనేది మేజర్ టాపిక్, వెరీ లెంతీ టాపిక్. ఈ టాపిక్ ఎప్పుడైతే రిమూవ్ చేశారో ఆటోమేటిక్గా మీకు ఉన్న సిలబస్లో ఒక 25% తగ్గిపోయినట్లే. కానీ బేసిక్స్ ఆఫ్ ఆప్ యాంప్ అనేది ఇంపార్టెంట్. ఆపరేషనల్ యాంప్లిఫైర్ని డైరెక్ట్గా మెన్షన్ చేయాల, కానీ యూ కెన్ సీ ఇన్ ద సిలబస్ స్మిట్ ట్రిగ్గర్ ఇచ్చాడు. స్మిట్ ట్రిగ్గర్ ఈజ్ అన్ అప్లికేషన్ ఆఫ్ ఆప్ యాంప్. ఆసిలేటర్స్ ఇచ్చాడు, ఆసిలేటర్లో కూడా వీ విల్ హ్యావ్ ఎ లింక్ అప్ విత్ ఆపరేషనల్ యాంప్లిఫైర్ ఆసిలేటర్స్. ఓకే, ఇన్ ఫీడ్బ్యాక్ యాంప్లిఫైర్స్ ఆల్సో దెర్ ఈజ్ ఎ లింక్. అంటే అప్లికేషన్స్ ఆఫ్ ఆప్ యాంప్ కంప్లీట్ ఫుల్ లెంత్ స్టోరీ ఆఫ్ ఆప్ యాంప్ ఈజ్ నాట్ నెససరీ. బేసిక్స్ అనేవి ఖచ్చితంగా నేర్చుకోవాలి. ఓకే, సిలబస్లో లేదని చెప్పేసి వదిలిపెట్టొద్దు చిన్న, రైట్. అండ్ డయోడ్ సర్క్యూట్స్, ట్రాన్సిస్టర్ బీజేటీ అండ్ ఇట్స్ బయాసింగ్, అండ్ ఫెట్ అని మెన్షన్ చేశాడు. అంటే you have to study JFET as well as a MOSFET. JFET and MOSFET syllabusలో ఉన్నా లేకపోయినా you can find in the previous year public sector like your GENCO, TRANSCO, AP and TS papers మీరు చూస్తే you can find the questions here and there from the operational amplifiers, JFET and MOSFET, right, in spite of the syllabus. Okay, right guys, coming to the important questions and model questions I have selected. ఇక నేను ఇచ్చే క్వశ్చన్స్ ఏంటంటే కొన్ని క్వశ్చన్స్ మైట్ వీ హ్యావ్ లైక్ సాల్వ్డ్ ఇన్ క్లాస్ రూమ్ ఆల్సో, బట్ హియర్ ఇన్ లైవ్ సెషన్ వీ కెనాట్ సాల్వ్ హండ్రెడ్స్ ఆఫ్ క్వశ్చన్స్. సో ఐ విల్ ట్రై టు గివ్ యూ మ్యాక్సిమమ్ నెంబర్ ఆఫ్ క్వశ్చన్స్ అండ్ ఐ విల్ ట్రై టు గివ్ యూ ద డిఫరెంట్ క్వశ్చన్స్, ఓకే, వితౌట్ రిపీటింగ్ ద క్వశ్చన్స్ విచ్ హ్యావ్ ఆల్రెడీ సాల్వ్డ్ ఇన్ ద క్లాస్. అండ్ ద ఫంక్షన్ ఆఫ్ JFET, జంక్షన్ ఫీల్డ్ ఎఫెక్ట్ ట్రాన్సిస్టర్ లేదా మాస్ఫెట్ అయినా ఫంక్షన్ ఓవరాల్ మోడల్ ఈజ్ సేమ్. ఐ థింక్ యూ రిమెంబర్ దిస్. బీజేటీ ఈ ఫంక్షన్ అడిగినప్పుడు ఆర్ బేసిక్ బిహేవియర్ అని అడిగినప్పుడు యూ నో నీడ్ టు వరీ అబౌట్ ద ఫీడ్బ్యాక్, షంట్ సిరీస్ ఆర్ వోల్టేజ్ సిరీస్, వోల్టేజ్ షంట్, కరెంట్ సిరీస్, కరెంట్ షంట్, ఇట్లాంటి ఫీడ్బ్యాక్తో సంబంధం లేకుండా ఓపెన్ లూప్ని అజ్యూమ్ చేసుకోవాలి. దెన్ ఆప్ యాంప్ అనుకోండి, ఫర్ ఎగ్జాంపుల్ వోల్టేజ్ కంట్రోల్ వోల్టేజ్ సోర్స్, దిస్ ఇస్ ద ప్రీవియస్ ఇయర్ క్వశ్చన్ ఆఫ్ కోర్స్. ట్రాన్సిస్టర్ అనుకోండి, కరెంట్ కంట్రోల్ కరెంట్ సోర్స్. అండ్ ఫెట్ అంటే either JFET or MOSFET, voltage controlled current source, because the drain current ID is a function of voltage, gate to source voltage VGS, right. So voltage controlled voltage source. Not only answer the question, మీరు ఈ ఇచ్చిన క్వశ్చన్కి ఆన్సర్ రాయడమే కాదు, రిమైనింగ్ ఆప్షన్స్కి క్వశ్చన్స్ కూడా గెస్ చేయాలి మీరు. ఓకే, వోల్టేజ్ కంట్రోల్డ్ కరెంట్ సోర్స్, because in the JFET ID or IDS is equals to IDSS into 1 minus VGS by VP whole square. No need to write entire expression. This is the input current and output current, dependent current, and this is a independent voltage source. Gate to source voltage is the input and drain current or drain to source current is the output current. So I'm writing here. I'm simply writing a field effect transistor. It can be JFET or MOSFET. Even MOSFET also. mu n COX W by L into VGS minus VT into VDS minus VDS square by 2. Their voltage, effective of course gate to source voltage, will drive the drain current ID. Okay. And current controlled current source, example, current controlled current source, IC is equals to beta IB, output current is equals to some constant into input current, BJT. Current controlled voltage source. This current control voltage source we have to design with the circuit by using op amps. For TS AEE students, we have discussed it. CCVS, VCCS, VCCS and CCCS, all the designs we made in feedback amplifiers. It is a circuit, not a particular device. And voltage controlled voltage source, it can be an operational amplifier. V naught equals to open loop gain into V plus minus V minus, non-inverting terminal voltage minus inverting terminal voltage. Okay. Anyways, for this question answer is voltage controlled current source. The voltage gain of a common emitter amplifier. Voltage gain of a common emitter amplifier. What is the general voltage gain relation? It is depending upon the type of model we are considering. Directly proportional to current he has given, collector current, base current, that means we better to choose a pi model. I think you may have done this type of questions also. What is the voltage gain relation? Minus GM into RC. Voltage gain relation is minus GM into RC approximately, or otherwise minus GM into RC parallel RL. What is a transconductance GM here? Transconductance GM is equals to collector current IC, DC current, okay, divided by thermal equivalent voltage VT. VT is a constant. That means what? Finally, voltage gain is proportional to DC bias current, IC DC or IQ, ICQ or I bias, all are same. Directly proportional to the collector bias current. It is not inversely proportional or independent or proportional to square. No, these all are the wrong options. RC phase shift oscillator. What is a minimum number of RC circuits required to generate a phase shift of 180 degrees? We have discussed in RC phase shift oscillator, common emitter amplifier, transistor amplifier will provide 180 degrees phase shift. I am not giving the complete circuit, and then here we can have a what we call RC network, capacitor, resistor, capacitor, resistor, capacitor and resistor. This is a feedback network. Okay, there must be at least 3 units, because one RC network can give maximum of approximately, nearly, it is not exactly, approximately 90 degrees phase shift. Transistor will provide 180 degrees, the beta network should provide remaining 180 degrees to satisfy the Barkhausen criterion, 180 plus 180, 360 in phase. So that's the reason minimum we need 3 RC networks or RC blocks in the RC phase shift oscillator. Okay, right. Colpitt's oscillator uses. Colpitt's oscillator and Hartley oscillators we studied simultaneously, and these are the radio frequency oscillators. In the Colpitt's oscillator, if you see the feedback network, amplifier may be inverting op amp or common emitter transistor based amplifier, but the feedback network will looks like this. One coil and 2 capacitors. And this is a tapped capacitive network. 1 by SC1, 1 by SC2. Here we have a tapped capacitors. If it is a Hartley oscillator, there will be one capacitor and two inductors, but it was a tapped inductive network we have discussed. Right, so tapped inductor, tapped capacitor, Colpitts oscillator, tapped capacitor. And what is the frequency of oscillations? Do you remember? F is equals to 1 by 2 pi into root LC, L into C equivalent, L into C equivalent, C1 C2 by C1 plus C2. But question is given for only the network model, how they are connecting the elements, direct capacitors or tapped capacitors. Yes, it is a tapped capacitor network we are using in the feedback path. Okay, I am going for the next slide, guys. Very interesting question. The ideal Zener diode shown in the circuit has a reverse breakdown voltage of 6 volts. Vz is 6 volts. The power dissipated in Zener diode and output voltage is asking Pz and V0. Okay, let me log into the YouTube. Then I will see your replies, and meanwhile you please try to solve the problem and please give me the reply. ఎస్ చిన్న క్వెరీస్కి ఒక కాంటాక్ట్ నెంబర్ ఆర్ ఈమెయిల్ ఐడి ఉంటుంది, మీరు ఒకసారి ట్రై చేయండి. ఇనీషియల్ అండ్ సర్నేమ్ అండ్ నేమ్ రివర్స్ ప్రింట్ అయినా నో ప్రాబ్లం, బట్ ఒక వర్డ్ లేదా నేమ్ మిస్ అయితే ఇట్స్ మే బీ ఏ ప్రాబ్లమ్. ఐ డోంట్ నో ఎగ్జాక్ట్లీ అండ్ ఐ విల్ లెట్ యూ నో. మీకు రిప్లై ఇస్తారు, ఐ విల్ జస్ట్ లెట్ యూ నో. మీ మెసేజ్కి మీరు వీడియో కంప్లీట్ అయిపోయిన తర్వాత మళ్ళీ మెసేజ్ పెట్టండి, ఆర్ టీమ్ విల్ గివ్ యూ ద రిప్లై. ఇప్పుడు ఇది లైవ్ చాట్లో ఉన్న మెసేజెస్ ఉండవు. సో మీరు లైవ్ అయిపోయిన తర్వాత మీరు మళ్ళీ మెసేజ్ పెడితే అవర్ టీమ్ విల్ గివ్ యూ ద రిప్లై. చిన్న విన్ కుమార్, Chakra G, very good. Jeet Kumar G, very good. Right, correct answer. Let me solve it. By look at this problem, immediately students will solve this problem for output voltage first. And options also very tricky. Why? Because 5 volts is given in only one option. 6 volts. Vz has given 6 volts. So immediately students will think voltage across the Zener diode is 6 volts. So that's why obviously the output voltage is a parallel voltage. V0 will be 6 volts, Vz. And they don't find the Pz because 6 volts is given in only one option. They will select option A. Okay? But my dear friends, in this particular circuit, you have to verify whether the Zener diode is in reverse conduction state or cutoff state. I think you may have an idea. The Zener diode can act as a voltage regulator only in the reverse breakdown state, or we can call it as reverse conduction state. This is a VZ. If you give more than VZ or at least VZ, then you can see the voltage drop across the Zener diode is constant. Here it can act as a constant voltage source or voltage regulator. Okay, but in this zone, what is the status of Zener diode? Zener diode status is open circuit. Sir, how do you know, how can you distinguish these two zones? Based on VZ. If you see that circuit, remove the Zener diode temporarily, then what is the voltage at this point? Here we have 10 volts. Okay, here we have 10 volts. This is simply a potential divided network, am I right? This is simply a potential divider network. Potential divider network. Resistor values are same, 1K and 1K. Then what is the voltage at this node? 10 volts. Resistor values are same, 1K and 1K. Hence voltage at this node is 5 volts. Voltage at this node is 5 volts. This 5 volts is not sufficient to bring the Zener diode into breakdown state. Why? Because examiner provided VZ is equals to how much? 6 volts. VZ is 6 volts. That's why Zener diode is in open circuit, right? Cutoff state. There is no influence of Zener diode in this network. This is simply a potential divider network. Current passing through the Zener diode is 0 amperes. Okay. So from this analysis, output voltage V0 is equals to 5 volts. Why? Because it is just a potential divided network. If Zener diode enters into breakdown or reverse breakdown or conduction, then only output is equals to VZ, it would be 6 volts. Assume if it is 15 volts or 20 volts input, then definitely VZ will be 6 volts. I mean, Zener diode will enters into breakdown state and output would be 6 volts. But now output is only 5 volts. And what is the IZ? IZ is 0. Then what is the power dissipation? Power dissipation PZ is equals to, what is the, he is asking power dissipation also in Zener diode, VZ into IZ. As IZ is 0, power dissipation is 0, right? So that output voltage 5 volts, power dissipation 0. Power dissipation comma output voltage he has asked, right? So that 0 and 5 volts. B is the correct answer. Please observe. B is the correct option. I am changing the slide. For example, in this same circuit, just assume, okay, if this is 20 volts here, okay, assume this is 20 volts. Zener diode will definitely in conduction state. What is the voltage here? 6 volts, because VZ is 6 now. If you remove it, this is 10. 10 is much greater than 6 volts. So it can immediately bring the Zener into conduction. Once if the Zener is in conduction state, its voltage will be stuck at VZ, that is 6 volts. Output voltage 6 is the answer. Then I am assuming it is 20 volts, okay, 20 volts. Then what is the current? As it is 6 volts, load current 6 milliamperes. Load current 6 milli. 20 minus 6. 20, this voltage is 6 now. 20 minus 6 by 1K, 14 milliamperes. Entering 14 milli, and load current around 6 milli. So 4 plus 4, 8 milli is passing through the Zener diode. Then power dissipation will be 8 milliamperes Zener current into Zener voltage 6 volts. Then it will be the power dissipation. Like that we will have the solution. But here Zener diode is not in conduction state, it is in cutoff state. Temperature coefficient of an intrinsic semiconductor. These are the direct points you have to remember, guys. Okay. Intrinsic semiconductor and insulator also. exhibits, I have explained with proof, okay, negative temperature coefficient. Extrinsic semiconductor and conductors also exhibits positive temperature coefficient. And thermistor also exhibits negative temperature coefficient, sensistor positive temperature coefficient. Like that I have given the table after completion of explanation of why extrinsic is PTC, intrinsic is NTC in the class. Okay. Okay, what is the question? Temperature coefficient of an intrinsic. You can find these questions more than 5 times in the previous year papers. Okay. Intrinsic semiconductors, negative. It's given simply negative. Temperature coefficient, it is not about a what we call charge of the body. Okay. Under thermal equilibrium semiconductor, thermal equilibrium semiconductor, the ratio of number of holes to the number of conduction electrons. Conduction electrons means what? Free electrons. And if you recall the mass action law, this is the exact statement you can find there. Number of electrons are equals to number of holes. Electrons in conduction band equals to number of holes in the valency band. Number of free electrons. Number of electrons in conduction band means number of free electrons is equals to constant. Of course, it is Ni, intrinsic constant. But he is asking the ratio. So, holes to electrons ratio is 1 only. All our previous year questions, engineering services, ISRO, and some of the questions are from GENCO and TRANSCO. Majority of these questions from recent electrical engineering services papers. As per the syllabus, I have selected, guys, and I have changed some data also, some simple numbers I have just included in the numerical. N-type semiconductor, what is the doping material? Do you remember? Fourth group, silicon or germanium plus pentavalent will give you N-type semiconductor. Fourth group, silicon or germanium with trivalent impurity will give you P-type semiconductor. Third group, boron, arsenium like gallium, indium we have discussed, and priority orders we have discussed. Phosphorus, arsenic, antimony and bismuth are the pentavalent impurities. Fourth group is also called as tetravalent, but question is given only about the material. N-type semiconductor doping material is. In order to get N-type, we need to add or use a dopant material from the fifth group element. Fifth group means pentavalent. B. I am not only giving you the straightforward answer, I am trying to cover some relevant information, okay. So, you can find multiple, from the same screen you can find around 4 plus 4, 8 different questions. Material names, fifth group, phosphorus, arsenic, antimony and bismuth. Boron, aluminum, gallium, indium, third group. Third group is trivalent, okay, right. Fourth group is actually also called as tetravalent. Going for the next question. MOSFET biased in common drain configuration. Common drain is best suitable for designing a common drain amplifier is similar to common collector amplifier. I think now we can get the idea. Common source is similar to common emitter, okay. So, common drain is similar to common collector. This is a voltage follower. And I am writing the approximate voltage gain, approximately 1. Hence, we can also call it as voltage buffer. Voltage buffer. D is the correct option. Yes, Chakra, G, correct answers. Good, good. In an intrinsic semiconductor, there are holes in the material. Number of holes equals to number of electrons. Electrons in the materials are more than holes. Say mass action law. B, I don't give any explanation, okay? Holes, electrons, same. An n-type semiconductor. So, type of material is n-type. Positively charged, negatively charged, neutral are not used in semiconductor devices. We are using it in semiconductor devices, but you please don't go for the negatively charged, okay? We have discussed this in the topic of electrical neutrality. Electrical neutrality. The semiconductor materials such as n-type or p-type, here in this question he has given n-type. It can be n-type semiconductor or p-type semiconductor. Remember, any semiconductor electrically neutral. Any semiconductor electrically neutral. Without equation, how can we say that? If you say n-type semiconductor, minority case, electrons, holes, both are same. Majority case, donor ions, positive ions, and electron, negative charges, again same. The overall body charge will be 0. There is no negative temperature or positive temperature separately. I can give you time to solve this question. In this problem, I have given this for TS-AEE students, for the students who have completed their analog, and for AP GENCO students, I have given just a rough sketch of current mirrors because it is a part of operational amplifiers. And safe side, even just if you understand the mirror effect, if the transistors are connected back to back like this, NPN or PNP, base emitter junction should be merged like this, then the mirror effect can work. No need of any proof and research. So, according to the mirror effect, this current will reflect in the second branch. But the condition transistor should be perfectly matched. We call them as symmetrical and identical. Okay. Same type of transistors and properties should be the same. Assuming beta to be infinite. Beta to be infinite means what? It is integrated circuit, that's why you can have beta value high. Generally, we will ignore the beta. Beta ideal means beta tends to infinite. So, large beta indicates base current can be ignored. Collector current is same as emitter current. Without any error, this current can reflect in the right side. Okay, it is a current mirror, that's all here. So, voltage drops are provided, drop in diode to be 0.7. Find the current I out. You see, who will give you the direction for the current? Arrow mark always. That's it, very simple. This is the current in the branch, same current will reflect at output. But this is a junction, okay, base to emitter junction. But as it is a PNP, emitter to base junction. Arrow mark direction will give you voltage drop 0.7. This is the current direction, diode is forward biased, plus minus 0.7. You have to find the current I. So, the current I is equals to I out. Current I is equals to 5 minus drop across the junction of transistor 0.7 minus, you see, collector and base are short circuited. So, that is why we can take this node directly. Once if you reach this, you can come to this and the diode drop 0.7. divided by total branch resistance is just 1 kilo ohm. So 5 minus 1.4, 3.6. I is equals to 3.6 milliamperes. There are two diodes. China. Please verify. If you two diodes means this is a physical diode, this is a junction diode, right? If you do any mistake, you will get some other answer. 5 minus 0.7, just you will get 4.3. That is also there in the option. Be careful. And this is a direct equation. You know always emitter current, IE is equals to beta times zeta of IB. You should have this all these relations in your mind. IC is equals to alpha times IE. IE is equals to IB plus IC. IC is equals to beta IB plus 1 plus beta into IC naught. Common emitter configuration, collector current equation, right? Common base. What is the collector current equation? Alpha times IE plus IC naught. Emitter current IE is always greater than IC, which is again greater than IB. IE, IC, IB. B is the correct option, okay? IE, IC, IB. Transistor amplifier in the following configuration is called as emitter follower. Remember, common collector is having this many number of names. Emitter follower, voltage buffer, voltage follower, unity with respect to voltage gain, unity gain amplifier, okay? Common collector. I am not giving you the answers, only the straightforward answers. I am trying to cover the relevant extra bits also. BJT amplifier configuration act as a voltage buffer. Of course, sorry, actually question is repeated. Voltage buffer is also common collector. Voltage buffer, emitter follower, okay? Voltage follower, all are same, common collector. Transistor point of view, common collector, okay? Or FET point of view, common drain. FET, JFET or MOSFET point of view, common drain. In the below given network, the diode ideal closed loop voltage gain. Current entering into op amp is 0. You no need to worry about this resistor and its drop. It is a negative feedback circuit, virtual short is applicable without any complicated maths. You can simply write V out is equals to Vs, then voltage gain is 1. This is also unity gain amplifier, or output voltage is same as input voltage. Voltage follower, voltage buffer, impedance matching device, we have this many number of names for this. What is the answer? 1. Irrespective of this RL, okay, it can be anything. AV is 1. Lower half power frequency means what? Lower cutoff frequency. We have discussed. If something, like frequency response of RC coupled amplifier is something like this. After connecting multiple amplifiers, cascaded amplifiers, you may have the new frequency response like this somewhere. This is a new lower cutoff frequency FL dash, higher cutoff frequency FH dash. FH dash or new higher cutoff frequency FH dash is equals to FH into square root of 2 to the power of 1 by n minus 1. FL dash is equals to, what is the FL dash? 1 by lower cutoff frequency, okay, new lower cutoff frequency, 1 upon lower cutoff frequency of individual original stage into square root of 2 power 1 by n minus 1. Actually, I am sorry, instead of FH, FL, that fellow given F1, F2, no problem, okay. This is F1 and F2 has given, but generally it is FL and FH. After cascading, gain increases, bandwidth values will decreases. He is asking about F1, that means he is assuming it as F1 dash is equal to 1 by something F1 into something. So, 1 by, sorry, FL by lower cutoff frequency, original lower cutoff frequency of a single stage divided by this n value, 2 power 1 by n minus 1, it is divided by n whole value minus 1. It is not n minus 1, okay, whole value minus 1, okay, it is not visible properly, you see, whole value minus 1, you see, FL or F1 divided by square root of 2 power 1 by n minus 1, okay, it's printing mistake. N channel JFET has IDSS and pinch off voltage. What is the maximum transconductance? What is a transconductance GM? GM is equals to minus 2 IDSS by pinch off voltage into 1 minus VGS by VP. It is not drain current equation, okay. GM equals to dID by dVGS. Differentiation of ID with respect to VGS, we will get this expression, transconductance. Here IDSS constant, pinch off voltage constant, VGS is a gate bias voltage. VGS is what? Gate bias voltage. But he is asking the maximum transconductance, you know. In order to get maximum transconductance, gate reverse bias voltage or gate bias voltage should be removed. The channel width will be wide because it is JFET. So that when gate to source voltage VGS is equals to 0, GM will becomes a GM max, maximum transconductance, but notation wise it is actually represented with GM naught. This indicates maximum transconductance. It indicates maximum transconductance. So, the maximum transconductance GM naught is equals to minus 2 into IDSS 10 milliamperes by minus 5. So, options are missing here, no problem, you can solve it. Okay? GM is equals to 5, minus 4, plus 4 milliampere per volt. Okay? 4 milliampere per volt. He is not asking the transconductance, he is asking maximum transconductance GM naught. Four. Chakra, very good. In a class, while discussing this problem models, I have written S only. Okay, ampere per volt or 4 Siemens, MS milli Siemens. MS also we can write. Almost same question but a little different. The value of transconductance. Transconductance at bias voltage 0. That is what I have written here. Transconductance when bias voltage is 0 is nothing but what? Maximum transconductance. So, there also question is about maximum transconductance. If you find the statements like this, you no need to worry. Okay, right. Direct you will get 6 milliampere per volt or S is given milli Siemens. GM naught minus 2 IDSS by pinch of voltage. IDSS 9 milliamperes. Pinch of voltage, for negative pinch of voltage will be negative. Okay. For positive, I mean P channel pinch of voltage is positive but IDSS will be negative. So, at any cost GM will be positive finally. Pinch of voltage is minus 3. 3 into 2, 6. Milliampere per volt or Siemens. B. It is not the conductance, China. Who is this? Bandaru Trimurthulu. It is a transconductance. It is a transconductance. Okay. Formula I have explained, Nachina. Simple, yaar. We are having drain current ID equation. IDS is equals to IDSS into 1 minus VGS by VP whole square. Transconductance GM, it is not conductance, transconductance. Output current by input voltage. Okay. Transconductance is delta or dIDS by dVGS. If you differentiate this current equation with gate to source voltage, x square 2 into something like minus VGS by VP, assume it as X, if you differentiate it, minus 1 by VP. So, minus 2 IDSS by VP into 1 minus VGS by VP something. This is a transconductance formula. This is the transconductance formula. Please listen it carefully. But this is the transconductance will depending upon the gate to source voltage. Gate is reverse bias voltage in JFET. If you increase the gate, channel width will decreases. Even in gate characteristics curve, we have discussed it. Maximum transconductance will be obtained when the conductance is more, means when the current is more. Current is more, we can get the gate characteristics curve like this. You can find more current, ID equal to IDSS, if the voltage is, gate to source voltage is 0. So, bias voltage, if you remove, if VGS 0, this is the highest value of conductance. In that case, conductance can be called as maximum conductance. It is transconductance, okay. The transconductance GM will becomes maximum, that is the highest value in the device. So, when VGS is 0, GM will become GM naught, that is it. So, sometimes they can directly ask maximum transconductance and sometimes they will indirectly ask maximum transconductance. He is given transconductance, but he is saying voltage is 0, bias voltage 0. That means gate bias 0 means the GM will becomes GM naught, okay. In both the cases, formula is minus 2 IDSS by VP. Maximum transconductance, I will write the formula if you want. What is the GM naught? Maximum transconductance. If you remove this, minus 2 IDSS. This question is given in previous year AP GENCO also, okay. This is important model. Maximum transconductance minus 2 IDSS by VP. Calculations you do, no problem. Formula minus 2 IDSS by VP, right. He is asking indirectly the maximum transconductance only, that is why I wrote directly formula minus 2 IDSS by VP. Pinch off voltage is minus 3, IDS value 9 milliampere something, yeah, I have substituted that, we got GM value. Transconductance GM, just now I told you, na, this is the equation. Do not select the equation with square, okay. Minus 2 IDSS by VP into 1 minus VGS by VP. This is a ISRO, 1 mark bit electrical paper. Yes, very good. Ready. VGS 0, they will give you statement, okay. They will provide. Without providing the data, they cannot ask you, okay. You don't worry about it. They will create the problem. Don't worry, They will create the problem with the proper data. Definitely you can find some hint, okay. Either they will ask you maximum, otherwise transconductance with 0 bias means that is also maximum. Without maximum means they will provide VGS. Without VGS, how can we get the answer? No way. The bypass, actually the AC bypassing by CE in a common emitter configuration, do you remember this? With the derivation, we have discussed this. Emitter resistor RE to bypass the signal, we are connecting bypass capacitor. Emitter capacitor CE or bypass capacitor. Without bypass capacitor, what is the gain? AV is equals to minus RC by small re. AV is equals to minus RC by capital RE plus small re. This is a voltage gain relation with the bypass capacitor. We have derived it by using RE model, pi model, H model, RE and pi model. We have derived these relations. and this is without bypass capacitor. So by AC bypassing by CE emitter capacitor. In a common emitter configuration, C suffix E of course, in a CE configuration, increases the AC gain. Yes, by providing bypass, by bypassing the AC current means by using capacitor, indirectly should understand. With the bypass capacitor, without bypass capacitor, this is a gain, denominator value Re plus small re. But with the bypass, denominator value decreases, so gain will increases. Increases the AC gain AV, decreases the signal across base and something, okay. Increases the AC gain. Very good. Who is this? Bhaigesri. Yes, Maunika. Mahita. Mahita, you have given D. That is Re China. If emitter resistor Re, question is highlighted the emitter resistor Re, then Q point stabilization. We have discussed it in DC biasing. It is AC circuits. In the DC circuits, emitter resistor Re providing good stability of Q point. Q point means operating point. That is different story. Please don't confuse, okay? The given feedback amplifier topology. This feedback resistor R2, which is common between input and output, okay? I can't explain. Feedback amplifiers is a big topic, you know. We have shortcuts also. Please apply your shortcuts connected at input as well as output. So given is what type of feedback amplifier? Shunt and shunt type amplifier. Shunt type amplifier. That is not given in the options. Shunt is not given in the option. That means input side mixing point, output side sampling point, right? Shunt mixing means, this is a shunt mixing means current mixing. I am writing here, current mixing. What kind of sampling from the output side? Shunt sampling. In shunt we will take voltage sampling. I have given the table with 44 relations now. So if you don't find these two, one of these two answers, like what we called formulas, what I told you, you can take this combination. Voltage shunt type amplifier. Given is a voltage shunt. D is the correct option. An amplifier has a voltage gain of 120. That means indirectly he has given voltage gain, open loop gain, right? To reduce the distortion, he has preferred 10% of negative feedback. What is the gain of the amplifier? With feedback means closed loop gain he is asking. Direct answer, gain with feedback is equals to open loop gain by A by 1 plus A beta. Okay. What is the A value? 120. Divided by 1 plus 120, beta value 10% means 0.1. You please calculate it. Tell me the answer. You will get around 10, less than 10, na? Less than 10. I think 9.23. Please check. Okay. The diode in the circuit given below has on voltage 0.7, ideal otherwise the current in milliamperes in 4 kilo ohms resistor. Sorry, options are missing here. It's okay. Is asking this current I. So first you should understand that this is a simple bridge, you know. 2K by 4K, 3K by 6K. You please check the bridge, as you people are from electrical, or otherwise 2 into 6, 12, 3 into 4, 12, or 2 by 4, 1 by 2, 3 by 6, 1 by 2. Bridge is balanced. So, sorry, bridge is balanced, okay. So, current passing through this diode is 0. We can remove this branch completely. 1 milliamperes, (2K) and 4K. We have to find this current I. (3K) and 6K. What is the current division rule? I is equals to entering current 1 milliamperes into opposite branch resistance is how much? 9K divided by total resistance 9K plus 6K. Please give me the answer. .6 milli. Answer is 0.6 milliamperes. Yes, Monica, correct. Right, guys, it's already 1 hour. Try to practice the notes problem. These are the questions randomly selected to recall the things only. So you don't need to go beyond the notes, just notes and some of the PYQ. If you have time, better to go through electrical gate 1 mark last 3-4 years questions, better, okay, right. All the best, guys.